Continue on our merry way. Last day before break. We'll finish up the chapter 12 content. So first we're going to do a little converting. We've got a couple of points right here. And we want to express these points that are given to us in polar coordinates. We want to express them in Cartesian coordinates. Let's first get a sense of where they are in the coordinate plane. So this first point is a unit away from the origin, so it's on the unit circle, and it's at 2 pi over 3. So that puts it right there. So that's the point. 2 pi over 3, and 1 unit from the origin. We actually already know that point. It's on the unit circle. So we could use that shortcut, but let's do the math. So we know that the equations to go to from polar over to Cartesian, we're going to use x equals r cosine theta and y equals r sine theta. Going from polar to Cartesian is a lot easier than the other way. So we know what the point is that we're supposed to get. All we have to do, though, is plug in our r and theta. So cosine of 2 pi over 3, that's -1/2. And then y is r, which is 1, times sine of 2 pi over 3. Sine of 2 pi over 3 is √3 divided by 2. So this tells us that our point is -1/2, comma, √3 over 2. So that's a point that we already knew, but this is how we do it with our two equations. Second point here, -4, 3 pi over 4. So if we go to 3 pi over 4, so 3/4 pi, so 3/4 pi, that's going to be bisecting quadrant 2. But the r value is negative, so instead of being out here, we've got to go all the way through to the other side, and we're going to be down here. So that is the second point. So we go to 3 pi over 4, 135 degrees. R is negative, so we go the opposite direction, and we're going to go 4 units from the origin. So that distance right there is 4. We actually can do that one already too. If we were on the unit circle, what would the point on the unit circle be right there?
-√2, comma -√2.
Close.
Sorry, -√2 over 2, comma √2 over 2, with negatives on both of them.
Well, we're in quadrant 4, so positive on the first one.
Positive on the first one.
Positive first one, negative on the second one. And if you multiply that by 4, let's just get that little thing out of there. If you multiply this by 4, you can treat it like a vector and multiply each of these coordinates by 4. This is actually going to be the point down there. If you take the unit circle point, so this point is on the unit circle right there. If you take the unit circle point and scale it by your radial value, 4, you could do it that way. But we'll do it the regular math way. So the regular math way is using those two equations. So x is equal to r, which is -4, times cosine of 3 pi over 4. Cosine of 3 pi over 4 is -√2 over 2. Multiply these together, and we will get positive 2√2. So that's the x value, positive 2√2. And for the y value, we do the same thing. We do r multiplied by sine of that angle. And sine of 3 pi over 4 is positive √2 over 2. So we're going to get -4 times positive √2 over 2. Which is -2√2. So therefore, our ordered pair looks like that. So that direction is the easy direction because we have x and y isolated right here. And it's pretty simple just to plug the r and the theta in and evaluate. Going the other way is a little more tricky. So express the following Cartesian coordinates in polar. Usually the equations that we are going to use for this Pythagorean identity. So if we know x and y, we can solve for r. And the other equation that we use is that the tangent of theta is y divided by x. So those are the two that we use going from Cartesian over to polar, because we need r and we need theta. So when we look at this one here, r squared will be 1 squared plus root 3 squared. So r squared will be 4. And r is going to be plus or minus 2. The standard choice would be to pick the positive 2.
Because we're in what looks like first quadrant.
And we are in first quadrant. But you could pick a negative r into quadrant 3 and do the whole reverse thing. But we're going to go with the standard representation. So we're choosing r to be positive 2. And then if we want if we want to find theta, we're going to use tangent of theta is going to be y over x. And we know from the unit circle, tangent is the slope of the terminal ray. So at pi over 6, the slope of the terminal ray is root 3 over 3. At pi over 3, the slope of the terminal ray is root 3. So this is going to be, if we pick the standard angle, it's going to be pi thirds. And so therefore, our standard polar representation will be 2 comma pi divided by 3. And sometimes we'll put a little p down there just to emphasize that that's in polar coordinates.
And there's no symbol like that for Cartesian?
You could put a C. Put a C.
Would you want
Or an R for rectangular. You don't have to put it though.
Would you want it on the test?
No.
But you can assume that from the problem.
Yeah, from the context you would
But
know.
in general, like application terms, would you put that on there?
Not usually.
Okay.
Most people don't. From the context, you can usually tell.
Why are polar coordinates useful?
For Calc 3. For Calc 3, when you get into doing surfaces, there's 3 coordinate systems. There's the rectangular, and then the cylindrical, and then the spherical. And you need polar to get into the cylindrical and the spherical coordinate systems.
That's nasty.
There's going to be a lot of surfaces that are just hard to describe with x, y's, and z's. So you'll want to use r's, thetas. With cylindrical, you use r and theta like these for the domain in the xy plane, and then the z coordinate will give you the height.
What's the example
So
of a surface that's hard to describe in X, Y, and Z?
Cone.
Or like a torus or something?
Torus.
That's one of them?
Torus is hard. Torus is hard. Torus is hard. So let's take a look at this one. Now this one is one that we shouldn't actually even have to do the math. You should know instantly what it is. What is the r value? 9. And what is the theta value? 9?
No.
Theta?
0. I'm fine. 0. 0.
All right, let's draw a picture. So 0, negative 9. Isn't that on the y?
That's the origin. That's the origin.
So 1, 2, 3, 4, 5, 6, 7, 8, 9. We're down here. What's that theta value?
2.7.
Don't say 0, please.
2.7.
So if we're in radians, we would say 3 pi over 2. So we should be able to look right here and say, oh, r is 9 and the angle is 3 pi over 2. If we go into the standard form. Obviously, you could use clockwise angle if you wanted. Oh, there's all sorts of things you could do. But if we take the positive r value and positive theta value, where theta is between 0 and 2 pi, that's our standard representation. So if we do the math, though, we end up with this. How do you know? We end up with that, and we're going to choose positive 9. And then tangent of theta is, y over x. Right, y over x, undefined. Or I should say that, this is undefined. If you look at this equation, it's undefined. Do you agree? And we know that there's two places where tangent is undefined on the unit circle. It's undefined at pi over 2 and negative pi over 2, or if you swing it around this way, at 3 pi over 2. So we're going to choose theta to be 3 pi over 2. I should say tangent of theta is undefined, not theta. Theta is going to be 3 pi over 2 or pi over 2. Pardon?
It could be either.
So if we did choose pi over 2, what would r be?
No.
Don't listen to him.
Yeah, I said 0.
If we chose pi over 2 for our angle instead of 3 pi over 2, what would r be? So if you chose pi over 2, that would stick you up here, so you would choose -9. So that would be an alternative representation. But if we know that we're down on the negative y-axis, it makes more sense to choose positive 3 pi over 2. You could also choose, while we're talking about it, if you wanted, you could choose positive 9 and negative pi over 2. That's also true. You would go to negative pi over 2 and then out that direction. What about if you chose negative 3 pi over 2? What would that be? Negative 9. Right, because negative 3 pi over 2 would bring us all the way to the positive y-axis, and then we want to jump through and get down to there, so we choose a negative r value. So all of those are equivalent. But again, most of the time we want the standard where it's positive r, positive theta, and theta is between 0 and 2 pi, or 0 and 360 if you're dealing with degrees. So let's look at some curves. So polar has a benefit in representing certain curves. Some curves are really hard to represent in polar, but some curves are really easy. For example, a circle centered at the origin. What could be simpler? R equals a constant, right? That just tells you that we want all the points that are a units away from the origin. So in Desmos or one of your graphing calculators, if you go into polar mode and you graph r equals 2, you get the circle of radius 2 centered at the origin. Similarly, a line through the origin is going to be theta equals a constant. So if theta is 2 pi over 3, you go to 2 pi over 3, and you get all the r values associated with 2 pi over 3. These are the positive r values right here. The positive r values are there, and the negative r values would be down there. So these are positive r's, and these would be the negative r's. So r equals a constant, circle at the origin. Theta equals a constant, line through the origin. And if you graph the identity function for polar, so the identity function in Cartesian is y equals x, and you get the line through quadrant 1, the tilted line at 45 degrees. In polar, the identity function is going to graph a spiral. As theta gets bigger, you're wrapping further around, and as theta is getting bigger, r is getting bigger, so you're getting further away from the origin. So that'll graph a spiral. All right, so there again are the 4 equations that take us back and forth. These top two we typically use for going from r and theta to x and y. The second two we typically use x's and y's to get to r's and thetas. So let's take a look at some equations. So r equals -2 cosecant of theta. All right, the only functions that are showing up in these equations are sine, cosine, and tangent, and most importantly, sine and cosine. Those are the most important two up there. And if we look at this equation here, we say to ourselves, well, let's certainly get rid of cosecant. Right? We don't want cosecant in there. If we're going to use those equations, we need it to be sine or cosine ideally. And tangent might show up, but at least sine and cosine. And so we just start doing manipulations until we can match something in that box. And if we multiply both sides by sine down there, we see, oh, r sine theta is y. So there is our Cartesian equation. In other words, this polar equation graphs a horizontal line at -2. Right? And so if this was r equals 5 cosecant of theta, we'd get the horizontal line up at +5. So that's the form of a horizontal line in polar. So you can see now that in Cartesian, horizontal and vertical lines are going to be more simply described. They're going to look a little more complicated in polar. But you can still do it. It's just that the equations are a little more complicated. Similarly, let's go for this one. So here, once again, we don't want secants and cosecants and cotangents. We want sine, cosine, and tangent. So this is going to be 4 divided by cosine. And then we say to ourselves, let's manipulate. Let's do what we can so that we get a match with one of these functions in the box. And right away, we see that if we multiply both sides by cosine, we end up with a Cartesian equation, or rectangular equation. Those are synonymous. X equals 4. So that's how we graph vertical lines. If this said r equals -7 secant of theta, we'd have the vertical line over at -7. So those are how we draw horizontal and vertical lines in polar coordinates. Not as obvious as these rectangular or Cartesian equations. We're very used to those.
Cartesian is just so much simpler.
What's that?
Cartesian is just so much simpler.
If you're doing vertical and horizontal lines. But if you're doing a circle, that's way easier. R equals a constant. Instead of x squared plus y squared equals r squared. Right? R equals a constant is easier. And a tilted line through the origin, it's a little bit easier.
If you have r equals one term, is it either x or y and never both?
If you have r equals a function,
Yeah.
it can be both. It depends on the function.
If it's standard.
It depends on how we'll do another one here. It depends on how complicated the function is. So the function can be complicated enough that it has both. You can end up with both a sine and a cosine, so you can get an x and a y. You can have both. So we'll do a couple of them. So first, let's talk about circles in a little more generality. So if the circle is centered at the origin, it's just r equals a constant. Simplest circle. Right at the origin, r equals 2, circle of radius 2, as is r equals -2. R equals -2 is also circle of radius 2 centered at the origin. So r equals a constant is always a circle at the origin. And if we want to shift our circle, it's going to look like this. Here is a shifted circle. So the A and the B are going to correspond to the center of the circle. And if you have both a cosine and a sine, and these coefficients both have a 2, both of them have a 2, then you're going to get a circle at A comma B. We in this class are going to focus more carefully on just the ones that are shifted in one direction instead of both directions. But you can't shift them in both directions, right there, really easy. But the ones that you need to know for the test are these ones. The ones that are tangent to x or tangent to y. And so let's go ahead and just notice that the radius of the circle is going to be A. So that's going to be the radius right there for both of these. That'll be the radius. So 2A is the diameter. So the total coefficient out in front is the diameter. Half of the front coefficient is going to be the radius. And if it's a sine, it's shifted in the y direction, so it's going to be tangent to the x-axis. If it's a cosine, it's going to be shifted horizontally so that we're tangent to the y-axis. And if this was a negative, it would bounce to the other side of the x or y axis, depending on which one you're dealing with. So if you go into Desmos, you can play around and get a really good idea. So there's 4 sine of theta. It's tangent to the x-axis. It's shift. The way I remember it, sine is a y-coordinate, so it's shifting in the y direction. And it's going to have a diameter of 4 and a radius of 2. So if we make this -6, it's going to bounce it down below. We'll have a radius of 3. So the radius is always half the absolute value of the coefficient. Question?
What happens if you double the angle inside sine?
All right. So let's make this 3. And so if we come in here and do something, if we put an even number in front, we will get a rose with 2 times that coefficient's petals. If it's even, 2 times the coefficient's petals. If we put an odd, we will get that number of petals. So odd, if you graph this function from 0 to 2 pi, you will get 10 petals. It's just that they're aligned on top of each other. If you graphed it from 0 to 2 pi, it's that each point is plotted 2 times. So if we go to the even coefficient of the angle, you will always get all the petals visibly there. And if you went from 0 to pi instead of 0 to 2 pi, you're only going to get half of it. You're only going to get 4 petals instead of the 8. So you don't need to know roses for the exam. If there's a rose on the exam, I will give it to you. But that is what you get when you have that situation. When you add a multiplier to the angle, you'll get a rose.
So you half the coefficient and then multiply it by what's in the sign, right?
So if you have nothing out in front, it's just smaller. The outside number is going to give you the radius of the circle.
Okay.
What if the coefficient's a fraction? Like less than 1?
Like if we have something like 0.5, and let's get all the way to 2 pi here.
A cardioid?
We are going to get something that's close to a cardioid. It's called a limishon. But we'll talk about that thing in a minute. We'll talk about it. Yeah. So if you do all sorts of strange angles, and back in the day you used to have to memorize all these things on how to graph all these things, but we don't do this to you anymore because now we have technology. So we graph most of the polar curves we graph with technology because it's so easy now. But
What happens if you square theta?
you figure it out on your own. we have to finish the content here. Okay, so circles, tangent to x and tangent to y. Let's try a few. So the best thing is for you to remember that a sine theta or a cosine theta is a circle tangent to an axis. So if you know that it's tangent to an axis, that's just going to help you sort of figure it out pretty fast. And if you use that idea that I mentioned, that sine is always associated with y, this is going to shift it in the y direction. If it's negative, it will shift it down. If it's positive, it would shift it up. That's a good way to get at it. How do we do the math? We go back to those equations. So with our equations, we had r cosine theta, r sine theta. Those were our 2 primaries. This sine theta has no r in front of it. Okay, so we need to somehow get an r in front of that sine theta. So the natural thing to do would be to multiply both sides by r. If we multiply both sides by r, we have that. And now we can do our conversion easily because r sine theta is, what letter is that, x or y? Y. And r squared, that's the Pythagorean identity, so that's x squared plus y squared. So now we have the equation in Cartesian, and we do what we learned back in college algebra to complete the square, to put this in standard form. And what would we add to both sides if we want to put it in standard form? What was that? I heard some sound like a gerbil maybe. So, well, what do we do? Divide by 2 and square? We add, what do we add to both sides? 4. take the coefficient of y in this case, divide by 2 and square, called down the road, whatever it was called, completing the something or other. Oh wait, we've done that in this class. You know how to do that. So there we go. There it is in Cartesian. The center of that circle is at 0, -2. And the radius of that circle is the square root of the right side. So that is the standard Cartesian form of it. So -2 is the center down there on the y-axis. The radius is 2. So pretty close. Pretty close. So there's our circle. So having the intuition ahead of time that it's going to be a circle just helps us. We know it's going to be a circle shifted down because it's a sine. And again, if we divide the coefficient's absolute value by 2, we'll get the radius. The radius will be 2. But we have to show the math. So this one we kind of know based on what I said. Cosine's going to shift it to the right or left. Because it's positive, it will shift it right. So it's going to shift this in the positive x direction. And the radius is going to be half the coefficient of the function, so it'll be 1. But if we do the math, we see that multiplying both sides by r will give us that. And what is r cosine theta?
X.
X. So here we have x squared plus y squared equals 2x. We go back to our college algebra again, put everything on one side of the equation. And then we complete the square by dividing by 2 and squaring. We add 1 to both sides. We complete the square, giving us x plus 1, nope, x minus 1. X minus 1 quantity squared plus y squared is equal to 1. So this tells us that the center is 1, 0, and the radius is 1. So 1, 0 is right there. Then we draw a circle of radius 1. So that's the graph of that one. Not too bad.
Can't we just look at it and go, you divide by 2, it's 1, and cosine's associated with x?
That's our intuition, but that's not the math. That's like how we can make sure we're sort of on the right track, but we've got to complete the square and put it in standard Cartesian form. This is what proves that that idea is right, that if we have that, we get the radius, and this is shifted to the right. Yeah. So that's good. That's how we build our intuition for sure. Okay, so now let's look at some randos. We've got a polar curve there. No clue what it looks like. But one thing we know is that if we want to convert to Cartesian, the only trig functions we can have are sine, cosine, and tangent. So let's at least get in here and start changing some things. So we could write cotangent as 1 over tangent. Tangent shows up over there, so we can do that. And then cosecant is 1 over sine. Okay. Sine is in the denominator on the right, so it moves into the numerator on the left. So let's go ahead with this. And r sine theta is y.
So y equals x over y.
Yep. So tangent is y over x. 1 over tangent is x over y. And we can then solve this. And this would be the parabola that opens to the right. X equals y squared. Centered at the origin, opening to the right. So describe the resulting curve. You know, on the test, I'll say graph it. That's what they mean. So we would graph that curve. So x equals y squared would be this. So that's what parabola, that's what, you know, a sideways horizontally opening parabola would look like? Ooh. A lot easier in Cartesian. But then we have this cute little equation there. Yeah?
So for what we did on Tuesday, that first chapter, will we have to graph those as well?
In that first section, remind me what we did in that section?
Parametrics.
Oh, yes, parametric graphs, yeah, now I remember. That was so long ago. Yeah, parametric graphs, you will have a parametric graph to do on the test. So they're going to be 4 or 5 from chapter 12. Parametric graph, perhaps polar graph, and then we're going to do a polar or parametric arc length, and polar or parametric area. That'll be about it.
What about hyperbolics in polar?
No hyperbolics, we won't do those. Is that good or bad?
Good.
Okay, so what's the equation for this one? R equals 2. What's the Cartesian equation?
X squared plus y squared equals 1.
Yeah, exactly. So that's the equation. So what you do here, instead of multiplying both sides by r, that won't help. If you multiply both sides by r, you would have r squared equals 2r, and then you're in a dilemma because whenever there's an r, you need a sine or a cosine. So that's not going to work. So what you do is square both sides. So if we square both sides, that's going to be the key, and then we know that x squared plus y squared is r squared. And so we know that we're going to get the circle of radius 2, centered at the origin. And there's our graph. Yeah?
Could you also redefine it to as 2 times cosine squared of beta plus sine squared of beta?
So on the right hand side?
Yeah.
So on the right hand, yeah, you could do that. Yeah, you could do that. So if you said that this is going to be 2 times the quantity sine squared plus cosine squared, then when you multiply both sides by r, then you'd have an r cosine theta. Yeah, you could do that. That would work. You could do it that way. Now we're going to get to the coolest graph that we're going to do in this section. Cardioids. Cardioids look like little kidney beans or hearts.
That doesn't seem that cool.
No?
No. I like the spiral better.
Spiral's pretty cool too. But I mean, to be able to graph that so easily, they're kind of cool. Okay, so the easiest way to graph a cardioid is to make a couple of observations. There are 4 key points to a cardioid, and they are always going to form a capital T. And so if you can find these 4 key points, then it's pretty easy to graph your cardioids. So for all of them, there is going to be these 4 key points that form a capital T. And those 4 key points are going to be on either the x or the y axis. So those key points, we can find the graph very easily. So before we get to graphing these, we have to ask ourselves, or at least we have to recognize that we need to know that it's going to be a cardioid if it has this shape, if it has this form. So first we have this piece. If you just saw that, you would say circle shifted horizontally, right? A cosine theta shifted horizontally. But if you add something or subtract, doesn't matter, plus or minus can be in front here and here, you can have all sorts of things with the signs. Signs don't matter. But if this and this are the same, those 2 numbers are the same, you will have a cardioid. So if you know you're going to get a cardioid, then you go ahead and try to find the 4 key points and then connect the 4 key points. So here's what we do. So let's take a look at the this first one here. So let's do this one first. So here's what we're going to do. We know it's a cardioid because it's in this form. We've got the 2 2's. And the plus and the minus don't matter. we have a number 2 here and a number 2 here, it's cardioid. And we only care about quadrantal angles. We only care about multiples of 90 degrees, multiples of pi over 2 radians. So here's what we're going to do. So we're going to do theta and then r. So theta, we're going to do 0, just the quadrantal angles. And that's it. Now we're done. Now if you want, you can go to 2 pi just to make sure that you're back to where you were at 0. But you don't need 2 pi. You just need 4 points. So we plug in 0. Cosine of 0 is 1. 2 minus 2 is 0. So that is the first point that we plot, the origin. First point. Second point, we plug in our pi over 2. Cosine of pi over 2 is 0. 2 minus 0 is 2. So then we go to pi over 2, rotate 90 degrees, counterclockwise, go to pi over 2, and we go 2 units from the origin. So there's our second point. Now we go to pi. Plug in pi, cosine of pi is -1. -1 times -2 is +2. 2 plus 2 is 4. So we go to pi, 180 degrees, and we go 4 units in that direction, putting us right there. Okay, so we're at pi, and the radius is positive, the radial value, so we go in that direction. And then our last point, 3 pi over 2. Cosine of 3 pi over 2 is 0. 2 minus 0 is 2. So we go to 3 pi over 2, which is, I thought I drew a point over here. Are my points vanishing somehow? So we go to 3 pi over 2, which is all the way down here, negative y direction. We go out 2 units in that direction. So that's our point. And again, if you want to do a fifth, just to confirm they didn't screw something up, you plug in 2 pi there. Cosine of 2 pi is 1. 2 minus 2 is 0. So you're back to where you started, back to the origin. Yeah?
Does the pi over 2 and the pi over 2, do they always have to be an equal amount away? So like,
2 of the points will always be an equal distance away. 2 of them. But it's not necessarily the same,
Yeah.
different card, but there will, and that's what's going to form the top bar of the T.
So it's always
You're always going to have that symmetry. Yeah. So if you graph your 4 points and you don't have that symmetry, you knew you evaluated one of them incorrectly. So if we do the other one here, so let's do that one. So theta and r. Again, just the quadrantal angles every time. This will do it for us. So we plug in 0, cosine of 0 is 1, so we get 0, 4. So 0, 4 in polar. In polar. That means theta equals 0, so that puts us on the positive x-axis. And then we go 4 out in the positive x direction. So that's point 1. Okay? So 0 is the angle, and we go 4 to the right. Pi over 2, cosine of pi over 2 is 0. 2 plus 0, 2. So now we go up to pi over 2, so we rotate up to the positive y-axis, and we go out 2 units. So that puts us there, point 2. Point 3, we plug in pi. Cosine of pi is -1. 2 minus 2 is 0. So this origin is being plotted now. We go over to pi. That's pointing in the negative x direction. But we go out 0, so it puts us right there. And then our fourth point down here, cosine of 3 pi over 2. Plug that in right there. Cosine of 3 pi over 2 is 0. 2 plus 0 is 2. So we come all the way around, swinging 270 degrees, 3 pi over 2 radians. We're down there, and we go 2 units in that direction, which puts us right there. And now when we draw our shape, it's usually easiest to draw half at a time. And just notice that when you go through these 2 outer points on the upper part of the T, you're bulging outwards, right? You're not drawing it, you bulge past that point and then you come around. So it's got kind of a more rounded shape than a heart would possibly have. So let's try. So those ones, cosine ones are always going to have this axis of symmetry horizontal, if these are cosines. And the sine ones are always going to have the axis of symmetry vertical.
So that second one didn't start at the origin, but its shape still revolves around the origin.
Right. So this one started at 0, 4, but if we were to graph it in Desmos or something, we would be going counterclockwise starting at that point. Yeah, Desmos will start plugging in thetas starting with theta equals 0. So that one is going to be plotted from there around. This one is going to be plotted from there around. So it's always going to be counterclockwise. All right, so let's do these sine ones. So same idea. Let's do this one first. So we plug in the theta, we calculate the r, and we just start going around the unit circle, quadrantal angles. We just need 4 of them. You can do a 5th if you want to confirm. And we just plug and chug. Sine of 0 is 0. 3 minus 0 is 3. So point 1, 0 radians, so we're going in the positive x direction. R is positive 3, so we go out 3 in the positive direction. So that is our first point. Second point, plug in pi over 2. Sine of pi over 2 is 1. 3 minus 3 is 0. So if we rotate up to 90 degrees, pi over 2 radians, we go 0 units in that direction. So that is our second point. And you already know, you could fill in the blanks really easily at this point. There's so much symmetry. If you already know that, we're going to see real fast that when we plug in pi, sine of pi is 0, 0. So we're going to go over to pi. I just said we have so much. Did I plug that in wrong? What's sine of pi? Sine of pi is 0, like I said, but I subtracted 0 from 3 and got 0. 0 from 3 should be 3. So in the pi direction, we're going to go out 3. That's going to be our third point. And now we know instantly that this has got to be our fourth point down here. It's always going to be the magnitudes added together. So 3 pi over 2, sine of 3 pi over 2 is negative 1. Negative 1 times negative 3 is positive 3. 3 plus 3 is 6. So in the 3 pi over 2 direction, we're going to go down 6. And then connect the dots. Okay, so you get the idea there. So let's do one from scratch. So let's do this one from scratch. So we have r and theta. So you all write down your 4 points. So write down your 4 quadrantal angles and find your 4 r values.
This might be a dumb question, but
Yeah.
will the A's always be the same?
They have to be the same in
Oh,
magnitude,
they have
or
to.
it's not a cardioid.
Oh, okay.
Yeah.
What would it be then?
Then it's going to be a limachon. So
What about nephroids and things?
a limachon, so if they don't match, so if you have something like 4 minus 2 sine of theta, this is a type of limachon where one side is flat. And if the inside is bigger, you're going to get a little loop in the middle. So these are all examples of limachons. A limachon is a cardioid that's got the dimple getting over dimpled and creating that little bubble, or the opposite. If this is less than the outside number, it's just going to flatten that side. And as it gets closer to this is not a circle. It might look like a circle, but it's not a circle. So as this gets closer to 1, it's going to get flatter and flatter. If we put a 2 here, put a 3 there, put a 4 there, then we have the perfect cardioid. So those are all limachons. Limachon. So what do you get for your first? Oh, I put my letters backwards. Usually we're going to do theta first. It's easier to do theta and then r. So 0, pi over 2, pi, 3 pi over 2. What do we get for 0? 8. So this says 0 radians, that's positive x direction, we go out to 8. So there is 0.1. That's 0, 8. It's very easy to all of a sudden plot a Cartesian 0, 8, and you have your points screwed up. So if you don't get the perfect capital T, just double check that you did the polar right. Pi over 2, what's going to be our R value? 4. So we rotate up to pi over 2, and we're going to go out 4, so there is 0.2. Now we rotate to pi, plug in pi, what do we get? 0, so we're going to be right at the origin. And then we rotate all the way down to 3 pi over 2. Cosine of 3 pi over 2 is 0. 4 plus 0 is 4. So we're going to be out 4. So then the hard part is connecting them. Just remember that when you sort of bulge out as you're doing it, it's much easier to graph half of it at a time. Bulge it out a little bit. It's not too bad. That looks perfect. If I could only do that every time. All right, so how about this one? So same thing. So start finding the R values here. Practice makes perfect. What is that first R value? 2. So 0, 2 in polar is 2, 0 in Cartesian. Everyone follow that? So we go 0 degrees, so positive x-axis, and we go out 2. So 0, 2 in polar is 2, 0 in Cartesian. What's the R value for pi over 2? So at pi over 2, sine is 1. 2 minus 2 is 0. So we're going to get the origin. Rotate to pi, sine of pi. Sine of pi is 0, so we end up with a 2. So we're going to be 2 in the pi direction. And then we keep rotating all the way to 3 pi over 2. And we get 4. So there's our capital T. Now we just have to connect them. And again, if you do half at a time and bulge out past that point, it's going to be a pretty decent graph.
Oh,
So there's,
Desmos loves us now.
how sweet. Desmos loves this. All right. Any questions on cardioids? So we've done lines, circles, and cardioids. Those are the ones that you need to know how to do by hand. Lines, circles, and cardioids. And the circles are tangent to x or y axis, not the general circle, or at the origin.
Can we call this getting our cardioid in?
You can! Yeah! Jose, you gonna like that one?
That was so bad.
That was so bad, it was good.
No.
Now, I did one semester, I had a student ask if instead of calling it a cardioid, if we could call it a gluteoid. I was like, you want to call it a gluteoid? If you want to call it a gluteoid, you can call it a gluteoid.
Why are they called cardioids?
Because it looks like a heart. I guess they just chose cardioid versus gluteoid. Gluteoid would be offensive to some. Probably not college students. Okay. Let's do calculus now.
When were the lines? Were those, did we cover?
We did the line through the origin. So theta equals a constant is a line through the origin.
Okay.
So theta equals pi over 6. We go to pi over 6 and then graph the line through the origin of pi over 6. Yeah. So now the calculus. Calculus of polar curves. So there is dy dx. It looks very much like the parametric dy dx looked. Remember the parametric dy dx, we said that dy bless you, was y prime of t over x prime of t. Right, that was the parametric way. Same idea though. Instead of y prime of t, we just have y prime of theta over x prime of theta. So it looks the same. Same concept. Now, the question though that is going to get tricky when we do dy dx, which is the slope of the tangent line, what will be much easier in the long run is if we, in order to find these, it's going to be much easier if we convert to parametric. Because when we have our polar equation, remember our polar equation is r equals a function of theta, like r equals 4 plus 4 sine theta or something. So trying to find these can only work if we write the x and the y in parametric form first. So remember that our equations to convert, we have y equals r sine of theta, and we have x equals r cosine of theta. So in order to take our polar curve is x equals, so polar is r equals some function of theta, like r of theta. So in order to convert from this polar over to parametric, we go to these two equations, and all we do is replace the r with whatever it's equal to in terms of theta. So we just replace the r, this r we're thinking about as a constant, right? If we write x equals 2 sine theta, or x or y equals 2, if we write x equals 2 cosine theta, or y equals 2 sine theta, we're thinking of that r as a constant. And we saw that it was the radius of the corresponding circle. So we replace that r with the function of theta that it is. So let's see. It may sound complicated for 1 minute. It will be uncomplicated in 5 seconds. So x is equal to r cosine theta. Y is equal to r sine theta. So those are our parametric equations for a circle. And now let's just replace the r with the function that it's equal to, so that we have x equals 2 cosine theta times cosine theta, which means 2 cosine squared theta, and y equals 2 cosine theta times sine theta. So this is our polar curve. We know that that's a circle of radius 1 shifted to the right. There is the parametric form of that circle.
That's way more complicated.
Once we have that, it is more complicated. Once we have the parametric form, then we can find dy dx. Now we just do what we did on Tuesday. Take the derivative of this with respect to theta, take the derivative of that with respect to theta, and then form y prime over x prime. Right? Dy dx is always y prime over x prime. So dy dx is always y prime over x prime. On Tuesday, it was y prime of t and x prime of t. Today, it's y prime of theta over x prime of theta. So whatever the independent variable is, we just differentiate with respect to that variable. So let's see if we can differentiate correctly, I believe. So let's find our derivatives. Let's do them right here. X prime. 4 cosine to the 1 multiplied by power rule?
I get it now.
Oh, good. And then chain rule times minus sine of theta. Do we agree? Do we agree? So x prime is that. Right, everyone agree? So power comes down, we subtract 1 from the exponent, and then we take the derivative of the base. The derivative of cosine is minus sine theta. Second one's going to be more complicated. We are going to treat this as a product. Here is the first function. Here is the second function. So we use the product rule. So y prime is going to be first derivative second. The derivative of the second is cosine. So first derivative second is 2 cosine squared. First derivative second plus the derivative of the first multiplied by the second. The derivative of the first minus 2 sine of theta times sine of theta, so we get minus 2 sine squared theta. So now we have our derivatives. And then dy dx, or the slope of the tangent line, is going to be the y's over the x's. So we're going to have 2 cosine squared of theta minus 2 sine squared of theta, all divided by negative 4 cosine theta sine theta. So that is the slope of the tangent line. We could cancel out a 2. If we divide a 2 out everywhere, and yes, if you wanted to use a double angle identity, you could, but you don't need to. But we can certainly divide out the 2. Do you want to use some double angle identities? No. No. Just notice the top is what? Cosine of 2 theta? Cosine squared minus sine squared is cosine 2 theta. Double angle identities, cosine squared minus sine squared is cosine 2 theta. And what's 2 sine theta cosine theta?
Sine of 2.
Sine of 2. So if you wanted to, you do not have to do this. You could do that. And that would be minus, is that sine or cosine? Excuse me, is that tangent or cotangent? Cotangent. So you could, if you were asked to, use double angles. I won't ask you to. Not on the test.
Okay,
So
so
you-
before we did that, that's a perfect example.
That's perfect answer right there.
Which one will Pearson take?
I should take either. Okay, so now the question said, just find dy dx. So there is our dy dx. So dy dx. Let's do an example here. Let's find dy dx. So because the independent variable is not an x, right? This notation dy dx, we could put parentheses if that was an x, but since it's not an x, we use this evaluation technique, say it's actually a theta. So if we want the slope of the tangent at pi over 2, we come in here, ooh, pi over 2, that's going to give us, well, you tell me what it's going to give us. What's going to be the numerator? Cosine of pi over 2? Did you say negative 1?
Yeah.
Everybody agree with that? Cosine of pi over 2 is 0. Sine of pi over 2 is 1, so we have negative 1 squared, which is negative 1. How about the denominator?
Wait, negative 1 squared?
Negative 1 squared.
Oh, okay.
Not negative 1 squared. Negative 1 squared. The negative is not in the square. So then, do we get a 0 on the bottom?
Yeah.
So what does this correspond to then on the graph? Undefined, so we get a vertical tangent line. So we get a vertical tangent at theta equals pi over 2. So theta equals pi over 2. What is the r value? So theta is pi over 2. So we know we're sitting up there on the positive y-axis. What is the r value? So where is this tangent line? Where is it tangent to the curve? So if theta is pi over 2, we come back up. What would r be when theta is pi over 2?
2.
2. So
Oh, so we're like on the edge of the circle.
So we are on, yes, exactly. So the polar point would be r comma theta. This is where we have a vertical tangent at this point. So the top edge of the circle.
Wait, no, isn't pi has a cosine 0?
Do we plug it in wrong? Cosine of pi over 2. Oh, cosine of pi over 2 is 0. Thank you. So where is this vertical? Oh, duh. Yeah. Where's the vertical tangent then?
At 0.
0. So it's on the side. So if we graph this circle we said was the unit circle, and it was shifted to the right. So here's our graph. And the point that we just found, this is 1, this is 2. This point right here is theta value of 0, r value of 2, so that's in polar. I'll put a p there to emphasize that's in polar because it certainly looks Cartesian. And there we have a vertical tangent. Draw a line, vertical tangent. Yeah. So what do you think the theta value is that corresponds to the obvious horizontal tangent on top of the circle? What do you think that r value might be?
No, wait, isn't it
1.
0?
In polar, it's 0, 2. In Cartesian, it's 2, 0.
Wait, so it's
In polar, r is 0 means, r equals, theta equals 0.
is it r
You're going in the
theta
zeta direction
comma
out
r?
too.
It's r comma theta, right? No.
Look back in the notes.
Yeah, it's
I'm pretty sure we write it like the distance
R comma
first
theta.
and then the
It is.
angle.
Yeah.
It's our comment.
You're
it's
overthinking it.
r comma theta, so this should be.
Yeah.
Did we? Oh, I feel like we wrote it wrong somewhere else then.
Yeah. Oh, thank you.
I feel like we wrote it
Down
wrong.
there we wrote it.
I think we wrote it wrong somewhere else.
Oh, wait, come on.
Here we did it.
So it's the same in both rectangular and polar, is that right then?
Yeah. Wait, hold on. Wait, what? Yeah. So they're equal, and I feel like somewhere else we did it backwards. Shoot. It should be r comma theta. Should be r comma theta. So r comma theta. So this point right here, we should be writing. So vertical tangent at.
Out to in the 0 direction.
So pi over 2.
That makes sense.
And then, wait, hold on, I'm confused. Let's take a break. Wait, so at pi over 2, we got undefined. So we said there was a vertical tangent at pi over 2. And when we plugged in pi over 2 there for theta, cosine of pi over 2 is 0. So the point on the curve here, so this is the place where we have a vertical tangent, and it corresponds to that point on the circle. But why did I put?
So it should be 2 comma pi over half.
It should be 2 comma. Yeah. How did we write that? I write that. Did I write that or did you?
No, wait, but R equals
But
0.
R
Sorry.
equals
Yes,
0.
oh my God, you screwed this up.
How did this happen? Is that what you wrote originally? Where did the 2 come from?
I don't know.
I don't know where it came from either. So, okay, so theta, plugged in theta is pi over 2, and my question to you was, where is this on the curve? We already know that theta is pi over 2, so then we plug it in up there and we get r equals 0. Oh, I think I plugged it in and got 2, and that's where the 2 came from. Okay, so that is the point on the curve where we have our vertical tangent. So the vertical tangent that's finding is pi over 2 comma 0 right there. Angle of pi over 2, radius of 0, there is the vertical tangent there. This vertical tangent, I saw the 2 and I was jumping over here. This is true, that there's a vertical tangent here, but what is this? R comma theta, R is 2, theta is 0, that's also a vertical tangent, but that's not the one that we found down here at pi over 2.
And it also just happens to be the Cartesian point too.
Yes, exactly.
Okay.
And now let's look one thing, and then we'll take our break. I feel like there was one place where we graphed a point. Wasn't there one place? I feel like there was a graph that we wrote. Well, I can look at the break. I can look at the break. I can look.
If you go down.
To what, down here?
Let's see which one it was. It was the one where we have the multiple ones.
I'll find it during the break. Let me hit pause on the thing, and I'll find it. You guys take 10-minute break. I won't take a break. Oh wait, I need a break. It's working. Okay, so I couldn't find another place where I flopped the r and the theta. So I think it was just that one place where I somehow flipped the r and the theta. But let me just summarize this one. So there are two. Okay, let's focus, boys.
Order in the chord.
Order in the chord. So this circle here, we notice that there's definitely two vertical tangents. And if we plug in theta equals pi over 2, or if we plug in theta equals 0, we will get a 0 in the denominator and a non-zero in the numerator. So we have two undefined slopes. One is at pi over 2, one is at 0. If we want to know where those vertical lines are on the circle, we take those two theta values, plug them in up here, and get our corresponding r values. So when we plug in theta equals pi over 2, we get r equals 0. So pi over 2 is the angle, 0 is the radial distance, so that puts us right here for that vertical tangent. Theta equals 0, plug it in right there. Cosine of 0 is 1. 2 times 1 is 2. So we get an r value of 2. So this vertical tangent is at 2, 0, where we're in polar. That's r, theta. Theta is 0, positive x, and we go out 2 units in the radial direction. Yeah?
So for all the tests, will you give us which theta values to look at, or will we do the same thing?
You will do one of a couple of things. I might have you graph it and then look at it and figure out what theta values you should plug in here, or it might be like this. Oh, right down here. We'll do one that's sort of like the one on the test.
So would it ask you where you want the vertical tangent?
Yes. So you know that a vertical tangent is where which part is 0? Bottom is 0 is vertical, and if the top is 0, horizontal. And if both are 0, both are 0 is indeterminate. So you would have to use a limit to figure out whether it's vertical or horizontal. So we'll talk about that in a minute.
On the last problem.
Yeah.
So, could that first tangent line on the,
Here?
yeah, does it have to go at the pi over 2 angle, or could it be at the 0 angle as well? Because you're at the origin, right? Does it really matter the direction, because you're just looking?
So if we're at the
right?
origin, it'd have to be here.
I'm trying to wrap my brain around it.
So if we're looking at the polar coordinates of that point, theta is equal to pi over 2, so we're rotating up to pi over 2, but we're going out 0.
Okay.
So if we go up to pi over 2, but then go out 0, we're still at the origin.
But it's like, if you don't move up in that, if you don't move in that direction, does
Then
it
it's-
matter at all?
If you don't move in that direction, then you're at the origin automatically.
Yeah, but that's what I'm saying. Could it be 0, 0 or 0, pi? Would it matter the direction? that
What
you're
matters is the value of theta that gives you the 0. Like one of the questions is going to be, what values of theta cause division by 0? So it's true that graphically there might not be, because if you graph 0, anything, you're going to be at the origin. So graphically, it might not matter if you're trying to find the origin. But when the question says, where is the denominator 0, then you're going to have specific values of theta.
But that could be anything too, because if the
No, there's only going to be 2 values of theta that cause this to be 0. Well, other than the plus 2 pi multiples. There's just going to be 2 values between, when we look at this equation, this graph is going to have a domain from 0 to pi.
okay.
I'll show you why in a minute. The domain is 0 to pi, and there's only going to be 2.
Oh, okay. Gotcha.
There's only going to be 2 zeros that happen in
So
that.
you're
you know.
just putting the 0 with that second one because it's slightly more, it's more convenient?
No, so this one is because 0 causes this denominator to be 0.
Yeah.
So
But
the
pi
2,
over 2 does that.
pi over 2 and 0, there's 2. So both of those, this angle being 0 corresponds to that vertical tangent. This 0 corresponds to that vertical tangent.
Okay, okay.
This vertical tangent at theta equals 0, we plug it in there, we get an r value of 2, so we're at theta, r comma theta, so theta is 0, positive x-axis, and 2 units away. Ari?
What was the question asking for again?
The question asked for the derivative, and then we evaluated the derivative here and saw that there was a vertical tangent. And then I made the mistake by plugging in pi over 2 there and getting 2 instead of 0. And then, so then I had drawn this vertical tangent, so then I wanted to follow up and confirm that, yes, there are 2 vertical tangents. This one corresponds to the left one, that corresponds to the right one.
So it doesn't matter if you say the vertical tangent is at point in polar or point in Cartesian?
Doesn't matter. Yeah, you could use either. So with this polar point here, if you wanted to convert it to Cartesian, you could do what we talked about a minute ago, plug it in right there and get it in Cartesian.
So would one of the horizontal tangent lines be something like square root of 2 pi over 4?
So if we set, so pi over 4 is going to cause the numerator to be 0. Does everybody agree? The numerator is 0 at pi over 4. Everybody agree? Because at pi over 4, sine and cosine are equal. At pi over 4, sine and cosine are equal. So cosine squared minus sine squared would be 0. So pi over 4 is going to correspond to that top 0. Yeah. Okay, let's go to the next one. So in general, so I just showed you how to find the derivative, the slope of the tangent line, using parametric. And the question that kind of comes up is, well, why do we want to convert to parametric instead of possibly doing it directly in polar? And here's the answer. That is what dy dx looks like directly in polar. That is not a formula you want to memorize. That's not a formula you even want to plug angles into. That formula is just super messy. So my recommendation is if you have a polar curve and you want dy dx, instead of memorizing a whole new formula, let's do what we did on Tuesday and use this form for the polar curve. So if we find x and y for the polar curve, right there, then we just do dy dx the same way we did on Tuesday, instead of having to do that as well as having to do that. Because that is a really hard formula to deal with. Now that formula, of course, will work if you want to do it, but it's going to be easier in the long run to convert to parametric and then do dy dx the way we just did it. That will be easier. So here's the new polar curve right there. We know that it's going to be some sort of rose because we have an angle that's multiplied with a coefficient. So this is going to be some sort of rose. And the question says, find the slope of the line tangent to the following polar curves. So again, here's how I think the best way to do this is. We want to, let's see, get the draw and then undo. So we want to go x equals y equals r cosine theta and r sine theta. So this one's going to be a little messy. Here's r multiplied by cosine theta. And then we do r multiplied by sine theta. So those are the parametric equations for this polar curve. So we take our polar curve, convert it to parametric, and then do dy dx like we did on Tuesday. Find y prime, find x prime, and form the quotient. So our quotient will be found by finding these derivatives first. So x prime, we have to use the product rule. So first function times derivative of second function. First function times derivative of second function.
Will you show us how to get x and y real fast? I forgot, or blank out.
X is r cosine theta and y is r sine theta. So there's r right there. There's r.
Oh, okay, gotcha.
So x is r cos theta, y is r sine
That makes
theta.
a lot of sense.
You see it? And so then the second part of the product rule, so this is first, derivative of second is negative sign, so the negatives cancel. First derivative second, plus the derivative of the first times the second. The derivative of the first. So derivative of cosine is minus sine. So we're going to have positive 4 sine of 2 theta times 2, chain rule, right? So we have to multiply by the derivative of the angle. So multiply by 2, so times 2. So I'm going to make this an 8, right there. So everyone following? Derivative of cosine is negative sine, so the negatives cancel. So it's going to be negative sine of 2 theta times 2, 2 times 4 is 8, times the second function. So there's our derivative for x, derivative for y, same process, first function, derivative second function, and then derivative of first function, which we just did above, right, derivative of that function times sine. Okay, so now we have the two components for the quotient, for the derivative. So dy dx is equal to y prime over x prime. So remember that x prime goes in the denominator. And do we see a common factor that we could cancel out of everything? 4. So let's do that while we're doing this. So we're canceling out of 4. So this is going to be minus cosine 2 theta times cosine of 1 theta plus, we canceled out of 4, so that will be 2 sine 2 theta times sine of theta. All that divided by x prime with the 4 canceled, cosine of 2 theta times sine of 1 theta plus, cancel out of 4, so 2 sine 2 theta times cosine theta. So there is our derivative.
Nasty.
Nasty. So that's the slope of the tangent line. Yeek. So this curve has a point on it that they would like us to find the slope of the tangent line at. So we would like to find dy dx. Notice that this derivative is only a function of theta. Right? There is no r in it. So all we need to do is plug in the theta. We don't really care about the r.
Oh, so that's in polar?
This is in polar. So this r value is important in that if you plug the pi over 2 in here, you should get 4.
Would you ever give us that point in rectangular and have us convert and then do the problem?
No, we'll just do it in polar. So pi over 2 goes in. What's cosine of pi over 2? 0. So I'm just going to highlight all the stuff that's going to turn into a 0. That's going to turn into a 0 because cosine of pi over 2 is 0. This is going to turn into a 0 because cosine of pi over 2 is 0. And then let's go ahead and look here. So in the numerator, what is sine of pi? 0. If we plug in the pi over 2 right there, we get sine of pi, which is 0. So that's also going to 0. So the numerator is 0. And what about the denominator? So pi over 2 in here, we get so cosine of pi is negative 1. Sine of pi over 2 is 1. So this all becomes 0. So what does that correspond to then? Horizontal tangent, so an HT at, so r comma theta. So theta, we have pi over 2 over there. That's our theta value. To get the r value, we come up to the original function. Plugging in theta equals pi over 2 gives us what? 4, which we already kind of knew. So that is going to be a horizontal tangent at pi over 2 comma 4. So in your mind, when you're visualizing pi over 2 comma 4, you're positive y-axis and you're 4 units away. So if we graph that function, we'll see that we have a horizontal tangent. Let's try this one. So these just take, you just have to be super careful with your derivatives. So x is r, so whatever the function is, your polar function, there's r, that's r, times cosine theta. And then y is r times sine of theta. So there is our polar curve converted to parametric. So that is the parametric form of the polar curve. So parametric means there's more than one, there's always 2 equations for us. So there's our parametric form. Now we want to find the derivatives. You have 2 choices. You could FOIL this out, distribute, and then take the derivative. Or you could just differentiate here and leave it as a product. Doesn't really matter. Both are going to be a little messy. Do you have a preference?
Maybe 4.
FOIL it out, distribute it. So this is going to be 4. And one shortcut, if you want a shortcut in terms of writing, if you're only dealing with sines and cosines, you could just use an S and a C instead of writing it all out for every step. It's totally, especially in the intermediate steps, it's totally fine. We could write this as 4 times cosine plus sine times cosine. And this is 4 times sine plus sine squared. If there's no cosecants and there's no secants and you know it's sine and cosine, that's a pretty nice little abbreviated way to get at it, especially when you start doing product rules. So the derivative of cosine is minus sine, so this is going to be minus 4 sine of theta. Sine times cosine, we have to use a product rule. So that's going to be first, derivative of second, the derivative of cosine is minus sine. So I'm going to make that a minus instead of a plus and put a sine squared. So that's first derivative second, plus the derivative of the first times the second. So that's cosine squared. And then for y prime, derivative of sine is cosine, so that's going to be 4 cosine. And then derivative of sine squared, pull the 2 down. So it's going to be 2 sine to the 1 times the derivative of sine, which is cosine. So there is our pair of derivatives. And then we can write our final answer for the slope of the tangent line. Y prime over x prime. There's no cancellation here, right? There's no 2 or 4 that cancels everywhere. So the numerator for the final answer, I'll write it out. 4 cosine theta plus 2 sine theta cosine theta. And the denominator is the x prime minus 4 sine of theta minus sine squared theta plus cosine squared of theta. So there is the derivative. So that tells us the slope of the tangent. We want the slope of the tangent at 3 pi over 2. So dy dx at theta equals 3 pi divided by 2, let's again highlight stuff that goes to 0. So, plugging in 3 pi over 2, what's cosine of 3 pi over 2? 0. Cosine 3 pi over 2 is 0. So all of these that have a cosine in them, all of those become 0. So the numerator again is becoming 0. So let's put that here. Now down below, sine of 3 pi over 2, -1. So we get a +4 there. +4 there, minus. Same idea here. Sine of 3 pi over 2 is -1. -1 squared is +1. And then we have that minus. So we end up with 0 divided by 3, which is 0. So this says, therefore, we have a horizontal tangent at r comma theta. The theta value is the 3 pi over 2. They already told us up here that if we plug in 3 pi over 2, we should get a 3. And sure enough, if we plug it in right there, sine of 3 pi over 2 is -1. 4 minus 1 is 3. All right, so there's one of the points. And this second point, that is in polar. So it's kind of, it's not obvious that it's in polar. But it's the same as the Cartesian form of it. So that's theta. So now let's do dy dx at 0. Theta equals 0. Let's again highlight the stuff that's going to go to 0. So plugging in 0. Sine of 0 is 0. So I'll use yellow for this one. So yellow for this one. Pink was this one. Okay. Sine right here, that's going to go to 0. That's going to go to 0. So let's see what we end up with. So in the numerator, we have 4 cosine of 0, which is 4. And in the denominator, those first two went to 0. And we're plugging in theta equals 0 there. Cosine of 0 is 1. So we get a slope of the tangent line 4 at that point 4 comma 0. So that's the slope of the tangent line.
And this is not a circle, right?
No. It's not a circle. It's not a cardioid. If it was for a cardioid, there'd have to be a 4 or a -4 in front of that sign. The two constants would have to match in magnitude. It's going to be a Limousin. Yeah, it's going to be the Limousin.
Leprechaun.
It's the leprechaun curve. The Limousin. Okay, so now let's get more general. So more general, here it says find the vertical and horizontal tangents. So find them. So we're going to do dy dx, and then we're going to figure out when the numerator is 0 and when the denominator is 0. So let's do that. So first we are going to convert to parametric. So there's r, that's r, multiplied by cosine of theta. And then y is r multiplied by sine of theta. So those are the parametric equations for this polar curve.
And this is a circle
That is a circle.
with radius 1
Correct. Shift in which direction?
down.
Down 1, yeah. Or down. So it's tangent to the x-axis. Okay, so let's find our derivatives. So x prime, we do first derivative second. Now this one doesn't actually ask us for dy dx specifically. It is saying where do you have horizontal and vertical tangents. We don't have to actually write out that big long fraction if they don't ask us for dy dx explicitly. We could just leave it as x prime and y prime. I'll tell you what I mean as we're going through. So first derivative second plus derivative of first is minus 2 cosine of theta times cosine of theta. So we get that. Y prime, first derivative second. So here's first derivative second plus the derivative of the first multiplied by the second. Yeah, Gage?
Couldn't you do either order for the product rule? 'Cause it's-
You can do the product rule either order, yep. In Calc 3 you can't because you're dealing with vectors, and so the product rule has to be done first derivative second plus derivative first second, because the commutative law of multiplication does not hold for cross products. Which is why I always do it that way, just to get in that habit, because in Calc 3 it has to be done in a particular way.
Can we simplify the x to -2? If the,
We can't, because if this was a plus we could.
well, the first one has a -2.
Wait, say that again?
They both have negatives in front of them. That would, if you factor out the negative. that
And
would-
cancel them? If we form dy over dx, yes.
Okay.
If we form dy over dx, yes. And what I'm saying here is that they're not actually asking us to write dy dx, so to write it all the way out explicitly, we don't really have to do it here.
But if we did, we could simplify.
Then we could
it.
simplify and cancel out the -2
Would
everywhere.
it help us at all to do it right now?
No. Not to answer this question. So what we want, so remember that dy dx is y prime over x prime. So which one gives us horizontal and which one gives us vertical? To be 0. Which one do we set to be 0 for a horizontal tangent? So y prime equals 0. This is going to generate horizontal tangents. So let's do that first. So we just take the y, set it to 0. Now, oh, question?
Wouldn't it be easier for the y prime to do a power rule?
You could do a power rule. Yep. Easier. Yeah, because these are now actually like terms. So probably it would be easier. It would be faster. If you see that this could have been combined and made -2 sine squared, yeah, you could definitely do that. And this would be -4 sine cosine. Yeah. Yeah, that's a lot. And you would get that directly then. Yeah. Okay, so y prime equals 0. So tell me where y prime is 0. So we're going to set y prime equal to 0. So that means 0 equals this. We could divide by the -4. If we have 0 equal to this, we're going to have 0 equals sine of theta cosine of theta. And what does that tell us theta has to be? So one of these would have to be 0. So when is cosine 0? Pi over 2. When is sine 0? 0. So this tells us this. And then your first question is going to be, well, aren't there more? And let me show you that when we find these thetas, we only want the thetas in the domain of the function. And so when you look at -2 sine theta, so r equals -2 sine theta, look. If we go 0 to pi over 2, whoops, pi over 2,
You said p to pi.
we only get half. When we go to pi, we get the full circle. So the domain for this curve is only 0 to pi. The entire graph is plotted in the interval 0 to pi. So theta here, we only are considering theta between 0 and pi. Technically, we would not want to include pi because that would overdo the circle by an extra point. So if we want just the exact circle, 0 to pi covers the exact circle. So we're only going to pick thetas that satisfy this that are between 0 and pi excluding pi. Question?
Is there like a mathematical way we can find those things? Or do we just have to know to be 0 to pi for any circle?
It really, so if the circle were centered at the origin, then it's 0 to pi. excuse me, 0 to 2 pi.
Oh, thank goodness.
If it's centered at the origin, so if you have circle centered at the origin, the only way that we're going to get around the entire circle is if we go 0 to 2 pi. Any of these curves that are kind of on one half of the plane, you know, they're not passing through both axes. If they're tangent to one of the axes, then it's going to tend to be 0 to pi. So the recommendation is do the graph. If you do the graph, you should be able to figure out if the domain is 0 to pi or 0 to 2 pi. What are you doing? What's happening over here? Are you singing? I hear strange noises. I don't know what's happening. So x prime is going to correspond to vertical tangents. So let's go ahead and find those. So x prime, right there, if we set it equal to 0, then we could do what Carter suggested originally was, hey, let's divide out the -2. So when we set x prime to 0, yeah, we can divide those out. And we're going to get sine squared plus cosine squared equals 0. Is that ever true? Something's fishy. Did we take the derivative right?
No, I don't think so. I think, isn't it positive?
Oh, this should be positive 2 sine right here. Because it's first times derivative second. Derivative of second is negative sine, so it makes it positive right there. Which then is going to make this, if we divide out just say a positive, if we divide out positive 2 here, then it's going to look like that. Okay, we know that this is a circle. So there better be 2 verticals and 2 horizontals. So we knew we did some algebra wrong. Okay, so when is this true? Well, isn't this the same thing if you add cosine to the other side and then divide? Isn't this the same thing as tangent squared of theta equals 0?
Oh, so pi over 4.
So if you, tangent is not,
Oh, wait, never mind.
not 0. Does everybody agree that we get to this equation? If you add cosine squared but then divide by cosine squared, you get sine squared over cosine squared, which is tan squared. Where is tangent 0? Tangent is 0 at 0. So theta equals, so again, we're only in this interval here. So tangent is equal to 0, and then where is it 0 somewhere else?
Wait, that doesn't make any sense.
Yeah, wouldn't it be
Yeah,
divide by cosine is 1?
Oh, that's going to be 1. Thank
So
you.
I was right.
Yeah, if that's what you said, then you are right.
Yeah. Or I said pi over
You said pi over 4. Yes. Yeah. I'm with you now. So pi, everyone. So if tangent squared is 1, doesn't this mean that tangent is plus or minus 1? Tangent of that is plus or minus 1, if we take the square root. So tangent is plus 1 at pi over 4. That is in our interval. And then where's the second one? 3 pi over 4. That's where it's equal to -1, and 3 pi over 4 is still in the interval. So these are going to be the 2 vertical tangents. These are going to be the 2 horizontal tangents. Does that make sense? So those are going to correspond to the top and the bottom of the circle and the right and the left of the circle.
Can you explain the domain again?
In a minute. Well, we've got some other domains that are going to come up, so it'll come out in the wash. We'll do. So let's look at this cardioid. So this is a cardioid. And let's graph this cardioid, and we'll see the domain here has got to be 0 to 2 pi for a cardioid, because the cardioid passes through both axes. Right? It goes around the whole thing. So anything that's lopped on one side of the y-axis or lopped on one side of the x-axis is just going to be 0 to pi. So cardioid, let's graph this. Let's do it all in one fell swoop. When we plug in 0, when we plug in 0, we're here. Sine of 0 is 0. -3 minus 0 is -3. So in the 0 direction, we go -3. So we come over to here. Now we rotate to pi over 2. Sine of pi over 2 is 1. -3 minus 3 is -6. So in the pi over 2 direction, we go -6. 1, 2, 3, 4, 5, 6. So we're down here. Now we rotate to pi. Sine of pi is 0. This is -3 minus 0 is -3. So in the pi direction, we go -3. So we're over here. Now we know where the last point has to be. We rotate to 3 pi over 2. Sine of 3 pi over 2 is -1. Positive 3 minus 3, 0. It's got to be right in the middle there. So here is our cardioid. This cardioid will have 3 horizontal tangents. It will have certainly 2 vertical tangents. Eek. And then we have to worry about the dimple here. So here is where we are going to get an indeterminate form. And if you do the limit, we will find that this is so steep here that we will get a vertical tangent. So for every cardioid, you will have 3 horizontals and 3 verticals, regardless of whether it's opening right, left, up, or down. So just know going in that we are going to find a 3rd vertical tangent. Question?
Are you telling me that the 2 horizontals on the top aren't at the same y value?
No, they're at the same y value.
Oh.
That is not drawn to scale.
But then why do we say there's 2 horizontals up top?
Because these are different points, right?
2 lines.
These are different points. The Cartesian equation for each of those lines would be the same, but the points of tangency are different, right? There's 2 points of tangency, 2 different points of tangency. You're right that the Cartesian equation of that line is going to be the same.
Okay.
Yeah, no. The cardioid is symmetric. It is not like that, no matter how I draw it. So let's... So the domain here is going to be 0 to 2 pi. So we do r cosine theta and then r sine theta. And our domain is 0 to 2 pi. Excluding the 2 pi so that we don't have any repeats. Now we have to find our derivatives. So again, this will get really messy if we rewrite dy dx, so let's just leave it as x prime, y prime, and then set those equal to 0. So we do first function times the derivative of the second function plus the derivative of the first function, which will be minus 3 cosine that. And then same thing down here. We're going to do first function, derivative of second function, plus the derivative of the first function times the second function. The derivative of the first function is minus 3 cosine theta times sine of theta. All right, so there are the 2 derivatives. And if we wanted to write out dy dx, we could, and we could cancel some common terms if we would like. But if the question doesn't ask us for a simplified dy dx, and it just says where are the horizontal and vertical tangents, then we don't want to rewrite that whole thing. So let's find the horizontal tangents. Horizontal tangents are where y prime is equal to 0. So we're going to set y prime equal to 0. So we're setting this whole thing equal to 0. Let's multiply it out. We get 3 cosine theta. And then here is going to be minus 3 sine theta cosine theta, but here is minus 3 sine theta cosine theta, so it's going to be minus 6 sine theta cosine theta. and we want to set this to 0. The only way we can get 0 is if we factor. So I'm going to factor out -3 cosine of theta, and then we are going to have this. So we need to set it up so that everything is multiplicative so that we can set things to 0. Okay, what are the theta values here? So theta equals, the only way these can be 0 is if either this is 0 or that is 0. So this is 0 exactly when cosine is 0, pi over 2 and so then we set sine of theta equal to -1/2. Sine of theta -1/2, 7 pi over 6 and 11 pi over 6. Now I just showed you a moment ago that we can only have, I should do this one in red because these are horizontal tangents and I did red up there for horizontal tangents. So there's one extra one. So let's just see what happens. Let's see what happens when we get to the next one. Will this work easily if I do that? Can I change the color to red? Yeah, I can. Okay. So now let's set the second one equal to 0. So let's go with purple on that one. So this is for vertical tangents. We're going to set x prime to 0. So we're going to look up there. We're going to distribute. So we're setting 0 equals, let's make that 3 sine of theta. And then plus 3 sine squared of theta. And then minus 3 cosine squared theta. The only way we're going to be able to solve this for theta is if we have the same trig function. So I'm going to replace this cosine squared with 1 minus sine squared so that we can solve for theta. So we'll end up with theta equals, we can divide out the 3, right? 0's on the left, so divide out the 3. So we're going to have sine of theta. And then here, when we divide out the 3, we're going to have sine squared minus 1. So there's going to be a minus 1. And then plus sine squared. So let's rewrite this as sine squared of theta. It feels like that's not going to factor properly, though.
I got something different.
It would be 2 sine.
Oh, that's going to 2 sine squared. Thank you. Okay, something fishy was there. So we have that. We have sine squared plus sine squared, so that's 2 sine squared. Yeah, thank you. There we go. So 2 sine squared of theta plus sine of theta minus 1. And that's going to factor into 2 sine of theta, 1. So both of them have a 1. We want the middle to be positive, so we're going to put the positive with the 1 that multiplies to the 2, -1 for the middle. So there are our 2. So we get that sine of theta is 1/2, or sine of theta is -1. So let's write down the theta values that generate those. What do we see? Sine of theta is positive 1/2. Pi over 6 and 5 pi over 6. Sine of theta -1. 3 pi over 2. Okay. This tells us that these are where the vertical tangents are. Those are automatic. And we have no conflict with these up here. So one of those is going to be redundant. One of those is not going to really correspond to a horizontal tangent. Let's see if we can figure out which one it is.
Will it be 3 pi over 2?
So 3 pi over 2, that looks like a horizontal tangent, right? 3 pi over 2, horizontal. I mean, now, it could be that there's some funny business with this, too. So let's just see where we are.
Pi over 2.
So what about if we plug in pi over 2? So if we plug in pi over 2, where are we? So if we plug in pi over 2,
Or vertical.
we're at -6. So that actually is where this horizontal tangent is. So
So do we just have like 2 redundant ones, or?
let's find out. So plugging in 3 pi over 2, what do we get when we plug in 3 pi over 2?
0.
So plug in 3 pi over 2, so we're down there, sine of 3 pi over 2, so we end up with 0. So 0 comma 3 pi over 2 puts us at the origin. Is there a horizontal tangent at the origin?
No.
No. So that one is out.
That's right.
Yes. And then the other two are going to correspond to those two. So the 7 pi over 6, most likely 7 pi over 6 is going to go backward. It looks like everything is going backwards. So 7 pi over 6 is going to correspond to this one, and 11 pi over 6 is going to correspond to that one with negative r values. So this is going to be figured out by plugging in the 7 pi over 6 right up there. So what's sine of 7 pi over 6? -1/2. 7 pi over 6 sine -1/2. So it's positive 3/2. So that's negative 3 plus 3/2, which is -3/2. So -3/2 for 7 pi over 6. And then for 11 pi over 6, plug in 11 pi over 6, sine is -1/2. So that's going to be positive 3/2, so that's also going to be -3/2. So these are going to be the 3 points of tangency where we have horizontal tangents. So at each of those 3 points, these points, so if we want to make these r comma theta, the same idea, we're just going to plug these in to the function and figure out what the corresponding r value is. So -3 minus 3 sine theta. I need to write it again. Okay, so if we plug in pi over 6, sine of pi over 6 is 1/2. So what are we going to get here? -3, so -5.5. So -11/2. Somebody double check that arithmetic. Sine of 5 pi over 6, 1/2, 2, 6. Everyone agree with that? So if we plug in 1/2 here, we're going to again get -3 minus 3/2. So it's -6/2. So -9/2. The math is hard. The arithmetic is hard. And then what do we get here? Sine of 3 pi over 2 is -1, so we get 0 there. So that's where so this one here, we had 0 and 3 pi over 2 twice. That one isn't true. This one is true. That's going to be a vertical tangent there. Yeah?
So will the indeterminate always be the repeated 0?
Yes. So if we get a repeated point, one of them will be correct, one will be incorrect, yeah.
Will we do this extensive of the problem?
It feels kind of long. We'll do one probably that's less long. Cardioids have a lot of vertical tangents. All right, let's go to our last topic here. So our last topic
That looks like some cursed version of a Riemann sum.
includes a Riemann sum.
Ah.
But in this class, to do Riemann sums, we just go like this. And then we're done with the Riemann sum. We go straight to the integral. We don't care about the Riemann sum. But here's the idea that we are going to look at with these. So with a polar curve, anytime you're trying to find an area beneath a curve, you're using some approximating geometric shape that you know how to find the area of. So, if we look at a polar curve here, so this polar curve is there, and it's emanating from the origin, and polar curves are always, you're always measuring radially from the origin. And so, theta equals a constant is going to be this boundary over here. Theta equals another constant is going to be the boundary over there. So theta equals a constant is a line through the origin. And so we have this region that's bounded by these two lines, theta equals alpha and beta. The approximating shape that we are going to use is a sector. That is our approximating shape, the sector of a circle, a slice of pie, slice of pizza. Slice, a slice of pie, a slice of pizza, whatever. Mathematically, it's called a sector. The area of a sector is 1/2 theta r squared. Now, when we're doing a Riemann sum, we do smaller and smaller subdivisions of the independent variable. The independent variable in regular functions is x. The independent variable here is theta. So instead of a theta, we think of this as a d theta. A d theta is going to give us a very narrow slice, a very narrow sector. And so that's where the delta will be. It's going to be with the theta. So what we're going to do is make this 1/2 r squared d theta. That is going to be the area of a tiny sector. So here we go. So this right here is the area of a sector. And the Riemann sum adds up n of those sectors to get an approximation. The bigger n gets, the better the approximation gets. And then we take the limit. And when we take the limit of the Riemann sum, we will get the exact area.
Looks like the washer method.
Sort of like the washer method if you have two curves. So if you had no inner curve here, you would be getting this full area there. If you had no inner curve. If you happen to have an inner curve, you've got to subtract off this inner area. You do the outer area minus the inner area, and then you'll get the area of just that part. So this is the generalized formula. So this one over here is going to calculate the inner area. And the outer area is the whole thing, minus the inner area is going to give you that. Right? So this is our key. That is the area of a polar region. We integrate 1/2 r squared d theta. And that's going to give us our area. So let's try one.
Shouldn't the 1/2 be outside?
Doesn't matter. Constants can float through, so you can factor it out if you want. We always factor it out at some point, so it's going to depend on maybe the r squared has a 2 in the numerator. Kind of depends, but it can be in either place. So now we have another polar shape here called a lemniscate.
What?
That is called a lemniscate or a lemniscate, depending on who you talk to.
Who comes up with these
Why?
names?
I don't know. I don't speak Latin.
Oh, it's Latin. I call it an infinity sign.
Or you could call it an infinity symbol. Or you can call it a sleeping 8, whatever you want to call it. Infinity symbol. Lemniscate. You want
The
to
limit as n goes to lemniscate of.
The limit as n goes to lemniscate. Okay, so it says find. So this is the equation that generates this graph. And it says we want to find the area of this right region here, this right eyeball. In order to find the region's area, we need to know the limits of integration. So let's start coming up with a little table of values. So we're going to plug in theta and get some r values. when we plug in theta equals 0, what is the R value?
1.
1. So we are right here when theta is 0. Okay. If you look at the polar paper behind it, it looks kind of like the origin will be plotted at what angle? Pi over 4. Let's check. Plug in pi over 4, cosine of pi over 2 gives 0. So this portion of the graph is going to happen between theta equals 0 and theta equals pi over 4.
So could we just double it up again? So
Yes.
Get rid of the 1/2 from the equation?
So we are just going to double it. We are going to find that area and then double it to get the area of the right side of it. And it's always best, you learn in Calc 1 that you really don't want to be integrating through corners and cusps and things like that. And in polar, sometimes it doesn't matter. But whatever happens when you're graphing, if you can get the simplest shape on an interval and then use symmetry, that is always the best rule of thumb. And so the simplest thing that we can do to get symmetry is we just do this top half, 0 to pi over 4, then we can double it and get that. And then if we wanted the whole area of the inside, then we would just double that again. So let's see what happens. So our area is going to be the integral from 0 to pi over 4. And we're doubling it. So I'm going to put a 2 out here for symmetry, and I'm just going to leave the 1/2 for a second. Now, yes, of course, they are going to cancel for sure. And then we are squaring the R function. The 2's cancel. And on the inside, we get cosine of 2 theta. That is integrable to sine of 2 theta divided by 2 using the reverse chain rule. 0 to pi over 4. Plugging in 0 doesn't give us anything. So all we care about is plugging in pi over 4. Put in the pi over 4 there. 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. So we get 1/2. So that is the area of one side of that lemniscate. So the full area of both of those eyeballs is 1. When you look at that, you would never assume that that has an integer area of 1 for both of them. All right, so we'll stop there. We'll finish the last slide and a half on Tuesday after break. We get a break for a week. Don't come next Tuesday. No one will be here. Have a good break. Do a bunch of math. Do a bunch of relaxing.
Thank you, Mr. Ross.
All right, have a wonderful break.